Okay. Very good. Okay. Thank you so much. Oof, now I'm the only thing that stops you from having lunch. That's the first thing I have to overcome here. No, just joking. So I will try to talk about something that is, how related it is to tensors, we will see. I mean, there's matrices inside, so matrices are tensors. But I use this idea of talking about the things for several reasons. One of them is that I needed to rethink something. I'll come to this in a minute. But also that I think it's a very complexity theory in general is very interesting. I'm not an expert in complexity theory, oh my God. But I came across a project that I really liked, and I thought it might be interesting, at least for the PhD students here, to hear something about this. And also because it touches onto my favorite topic, which is symmetry. So we all that teach lectures in high schools, universities, know that people lose attention very quickly. Or if you fall asleep, don't worry. You just have to bear with me the first 5 minutes and again the last 5 minutes, and the rest, fine. No, kidding. Just let me talk a little bit about symmetry in general and how this also relates to a talk that Luca is giving this afternoon. Where's Luca? Luca is giving this afternoon. So we all know that symmetry is a very deep mathematical concept that allows us, to make nice pictures, but it also allows us to understand things, structures. And as you will see this afternoon in Luca's talk, symmetry, or as you have already seen also in Henry's talk yesterday a little bit, symmetry is a concept that allows us to reduce complexity of things. For example, if something is very complex but has a lot of fundamental structures, symmetries, you understand such a picture much easier if you understand that this is symmetric, so you only have to look at the fundamental domain, for example, so it reduces complexity. But on the other hand, of course, also it creates complexity. So by symmetry, you can write something down very simply and then just say, well, by symmetry, this is you blow it up by having a group action. This is a little bit vague how I say this now. This is the philosophical part, so don't worry if you don't understand what I'm saying. But there's a dual side to this reduction, is that it actually also allows us to write down complex things very compactly and very interestingly. And this is a little bit the side that I want to touch on, so that I don't talk about the same things that Henry and Luca are talking about. Okay. Who of you has taken linear algebra? Everybody. Very good, very good. So I should, and this is also for the PhD students to learn, a talk should always start from somewhere where everybody's familiar. You all have seen the determinant, right? This is one definition of the determinant, and when you look at this definition of the determinant, what we're doing here is we are building, it's very compactly written, the way I write it here, but it's actually a very, 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 very long sum. How many summands does it have? Yes, very good, very good. So this is the easy question, so it's very, very good to answer these. Very good, because otherwise you'll be picked for the heavy one. So it's n factorially many summands that we have to evaluate if we want to compute a determinant. Or, who of you computes a determinant sometimes in their lives? Okay, Alexander, how do you compute a determinant? Exactly. So there is a method called Gaussian elimination that allows us to do this huge computation, n factorially many things, very simply. Okay. Gaussian elimination, for example. Very good. So one could play a similar game, write down a function here, and we make it actually much easier. If you remember in the first semester, I had this very much, like the sign, this definition, it was very weird, right? You would want as a student in the first semester linear algebra that this is the definition of the determinant because it's much easier to define, right? It's just you summing up overall the product, so no need for this sign. So, this is called the permanent. Maybe not everybody has seen the permanent, but this is also, it looks, it's the twin in some sense, or the evil twin, I don't know, Dr. Jekyll, Mr. Hyde, you know, of the two things that look kind of the same, but we will see that they're actually not the same. So we can hear an expert of combinatorial optimization. There is a funny combinatorial optimization or combinatorial problem that we will play maybe tonight in another instance. And it's the question like in how many ways can n married couples or n couples, PhD student, PhD supervisor, you think about whatever you want to see, be placed around a round table so that men and women sit in alternate places and no husband sits on either side of his wife. I know, this is exactly, this is very good, very good, very good, very good, very good. I like this. This is why we will play it tonight with PhD students. This is a classical problem that somebody put out there. This is called Problème des ménagers, ménage. And we wouldn't play this anymore today, of course, or we would play it with other with many more genders, maybe. You can cook up what you want. It's not important. It's not important. The interesting thing is that this problem, actually, the number pops out if you calculate a permanent. So the permanent that you calculate is the permanent of this matrix, where you take the all-one matrix and you substitute from it the identity matrix and this permutation matrix. Yes? Okay, now this is, and I wanted to say this talk will contain a lot of life lessons, you know, and one of the life lessons is never to do such examples. Very good. And the best way to learn lessons is to learn them the hard way, right? So then you all have felt with me, never do this example, no, joke by that. So this is, I mean, having an algorithm that can compute permanence can be useful. They turn up in combinatorial problems. Okay, they actually turn out in many places. So many combinatorial problems, countings can be phrased as evaluating permanence, Latin squares, tilings, perfect matchings, probability theory. Don't ask me too much about quantum field theory, ferromagnetism, coding theory. Permanence actually are very amazing things. So they are very, very unambiguous. They pop up in many surprising instances. So you might be faced one day in your life to calculate one. So let me, again, I'm not a theoretical computer scientist, and I don't want to go too deep into complexity theory, but let me just start with one distinction that is pretty interesting. So, I mean, we all have a notion of, I mean, everybody here in the room may have an idea what it means to be a hard problem. NP, P equals NP. I mean, we all have heard of these things. So what is important is when we talk about these questions, we normally talk about questions where we ask, do we have a yes or no answer? Does a solution exist or does a solution not exist? Is the number a prime number? Is the number not a prime number? I have a three-sat. Is there a solution? Is there an assignment of true or false to the clauses such that the whole thing is satisfiable? Right? So this is a yes and no answer. And there is something that is a little bit more interesting, or harder actually, is not only to ask yourself, is there an answer, is there a satisfiable assignment, yes or no, but how many satisfiable assignments do I have? Huh? Is this number a prime number? Is this number a composite number? Yes, how many factors do we, how many factorizations, how many, so all these questions, like when you ask not only yes or no, but you want to know how many, they are much richer. These are counting problems. And there is also an NP sort of thing for counting. This is what we call sharp P. So this is hard problems in counting. So where you don't only want to have yes or no answers, but but counting answers. And of course, I mean, they're believed to be harder. So we believe, so if I know how to count the number of factorizations of a number, if I know to count the number of satisfiable clauses, then of course I can decide if it's satisfiable or not. So this is, I mean, one include, and the other is believed to be strict. So these are really harder problems. Yes? No, so you can define it via Turing machine. So, but I mean, think of it as hard counting problems.
Where sort of like you would have at least like half of the paths sort of accepting, and sort of here you have sort of you count the number of paths, and so sort of by counting the number of paths which are accepting, you know whether at least half of the paths. It's like 1970.
It's 1979, to be exact. Exactly. That's so. If you this was defined by Valiland in 1979. And he proved that the permanent is the classical example of a counting problem, an evaluation problem that is Sharpie hard. And in particular, he proved not only that it is Sharpie, but also if you not only take any matrices, but you restrict to 0, 1 matrices. Okay, interesting. Permanent. Who has seen the permanent before? Very good, very good, very good. So we're getting so. So, but I mean, remember the game that we played? Yeah, exactly. And this was also the paper where he introduced this class. We don't have any Hungarian in here, only a Spanish person who claims to be Hungarian. No. So let me give a small Hungarian intermezzo anyways. So permanent versus determinant is actually going much back to the beginning of the 20th century, where Polya observed that, I mean, they look similar. So if Bernard has a 2x2 matrix, A, B, C, D, and he wants to compute the permanent of that. And then Polya observed, haha, I can just take a minus. Add 1 minus to this 2x2 minus here, yeah. And then I get back the determinant by computing the determinant to your matrix. I will get the permanent. So very easy. And then he asked, well, it's cheating, but if you know how to do this, then, I mean, math is often very clever cheating. No, it's, I mean, if you know, I mean, here you know a very, for all this is true for all matrices, so it's not cheating, it's essentially just, you know, a way of computing it by relating it to the determinant. And he asked in his article, so is this always possible also for higher matrices? So do we always get for a fixed n an uniform way to assign plus and minuses to be able to relate the determinant to the permanent? And I mean, so this appeared in some sort of journal with riddles, so in 1913, and I think the next issue already had the answer, saying, no. So by another important Hungarian mathematician, that's why it's a Hungarian intermezzo, Seger, answered, no, you forget about this, and you can immediately cook out a 3x3 example where it doesn't work. So you take the all ones matrix, and you see that the permanent of this is 6. And when you, however you assign pluses and minuses, it's not 6. So it will be always smaller than 6. Okay, so obviously, so one counterexample is enough. So of course, but you can, let me say, this is an interesting question. You can ask yourself, okay, now we maybe know that the same size is not sufficient. Couldn't we hope that I take a matrix, Alessandra gives me a matrix, she wants to know how we assign the tables tonight for the dinner with the PhD students and the supervisors, and she doesn't want to compute the permanent. I don't know how to compute the permanent, but maybe Monique has a clever trick to build up a 10x10 matrix instead of a 3x3 matrix. whose determinant would be the permanent. And this is a still very much ongoing question. I mean, can you build up matrices from the initial matrix in a not in a random way, but in a programmed way, such that you get back the permanent of your original matrix from the permanent. And if from the determinant, if you're able to find this, and if the size of the matrices that you need for that is not growing too quickly, you will be $1 million richer, right? So it's very unlikely that you find this, but anyways, this is just for you if you want to have some time during the talk and you're no longer interested. Okay, so this was permanent and determinant, and the important thing is to remember determinant easy, permanent hard. Now, this is interesting, but can we cook up something that a family of polynomials that sort of lie in between the determinant and the permanent? And this maybe it doesn't make sense for the moment, so let me with the introduction, and then I'll try to recapitulate this again. So first of all, remember that a group representation, if you've never seen this, just one slide. I mean, representation is you take the group, you let it act with matrices on a vector space, and the character of this representation is then just to every group element you associate a matrix, to the matrix you associate a trace, so to every group element you associate a number. So it's and this is called the character. So the character depends, of course, on the group and on the representation. Okay, character of a group. So we have the symmetric, and the symmetric group has characters. One character we have already seen two characters. We have seen the so-called trivial character. So that's that assigns to every element the one element, and through the trace, then the one is a number, so it assigns to every element the one. That's a character of the symmetric group. It's a character of every group. And we actually also have seen the sign. The sign also is a character, so it's a function that you define by having the group acting on a vector space, and you can on a one-dimensional vector space, whenever the number of how the sign is defined, right? So it's 1 or -1. Okay, very good. So characters actually are functions. I said from the group to the to numbers, to the number field, but actually, as you see, because I mean the trace is they're actually constant on conjugacy classes because you can multiply from the left and from the right, and then essentially the trace doesn't care too much about that. Carry on. So exactly, and amongst the characters, the important ones, or amongst the representations, the important ones are the so-called irreducibles. So they have a very nice connection to the conjugacy classes of the group. So they are exactly as many as the group has conjugacy classes, and they somehow tell you a lot about the group. And again, we have seen two irreducible representations of the symmetric group, namely those two are also irreducible because they correspond to one-dimensional vector spaces. So this was a lot of information. If you have never seen group theory, forget about it immediately. Just remember there is a fancy thing that assigns a function on a group that assigns to conjugacy classes some numbers, and that's done in a very fancy way that makes sense and generalizes the sign and the one function. And just with that at hand, the definition that I wanted to bring up makes a lot of sense. So you say, okay, I just take the definition of the determinant. That's the definition of the determinant almost. I just replace the sign by any character of the symmetric group. Okay. Okay. And of course, if I want to have the permanent, then I take the trivial character. If I have the determinant, I take the sign character. Okay? So this is how you define the immanent corresponding to the representation phi. Who has heard the word immanent before? Oof, still too many people. Okay. Very good. Okay. So let me just tell you a little bit about the, we have already seen partitions. So partitions is just a set of integers that sum up a set of ordered integers that sum up to a given number n. And we call the height of the partition the number of numbers that we add up. The size is n, and n minus the height is b of lambda. And you can also add partitions. Okay, that's not important for, I mean, adding partitions, you just component wisely add them. And if, yeah, so it's a little bit, it's just a formal thing, partitions, and you have to extend them. That does make sense, but that's fine. And it makes also sense to write them. I mean, you don't write repeated numbers, so you can also just abbreviate the 2 to 1, 1, 1, 1, 1 by 2 to the 2, 1 to the n minus 4. So, I mean, there's a compact way of writing a partition down, sort of that. I mean, this is just, I mean, here I can now let the n grow, and all of you understand what I mean by the sequence of, it's technically a sequence of partitions that we get in this way with growing n, but essentially, I mean, we can just write it down like this. That's all that I wanted to say here. Okay, so why do we care about partitions? This is also something that is maybe in a course in representation theory. So there are these fancy things, irreducible representations of the symmetric group. They are in bijection with the conjugacy classes of the symmetric group, and they are in one-to-one correspondence with the partitions of the number n. So if I talk about irreducible representations, the set of irreducible representations of the symmetric group Sn, I can parameterize them by partitions of the number n. Okay? And also very nice, I can visualize the partition with a Young diagram. I think we have also seen this. So just, I mean, instead of reading a definition, this is just, you really, it's a number of boxes that you say, well, you have 2 in the first row, 1 in the second row, and 1 in the third row. And if you have seen a Young tableau, then the definition of the conjugated partition makes a lot of sense. So you take this Young tableau, you flip it around, you get this Young tableau, and this again corresponds to partition. In this case, 3, 1. So you have a partition and a conjugate partition. And then again, if you're French and you do, then Young tableaus become complicated. If you're Russian, then they are even so. There's different notions for doing these things, but there's nice combinatorial objects that are in one-to-one, that characterize irreducible representations of the symmetry. Okay, why is this important for me? So here is the determinant. Here is the permanent. The permanent is associated to the trivial character. If I want to visualize the trivial character with Young tableaus, it's just a Young tableau with one long row. Sure. And if I want to visualize the sign representation, then again, this is maybe now arbitrary for those who have not heard about representation theory, then this is normally visualized with a one column of a Young tableau with one column. So it is very easy if I have one column, and it's apparently very hard if I have one row. So what is the natural thing to ask oneself now? Wow, I still have at least one person who figured it out. Okay, so the interesting normal thing to ask is, okay, so I mean, we can now really look, I mean, there's a natural order on Young tableaus. So you have, I mean, you have a natural sort of space in between the determinant and the permanent where you can ask yourself, okay, where does it get harder? And I mean, of course, this was not me who came up with this idea. study this for the first time. So this has already been studied in the 80s, right after Valiland. People like Hartmann, Barvinok, Bügerse, sort of have special cases where they say, okay, like if we have several rows and columns, so when does it get harder? Exactly. But there was only sort of partial results with special case, or like special ways of building up these partitions. Okay, now comes another life lesson for you to learn. So I got into this whole business because my collaborator Istvan visited Tromsø at some point, and he gave a talk about counting complexity. And I said, this is very interesting. I never thought about why counting is so much harder. And he has a nice book about it. So we started to discuss this a little bit. And we came about symmetries. And then we mentioned the determinant, why the determinant is easy, that it's not only all with Gaussian quadrant, but anyways. So we discussed this a little bit, and we thought, okay, we should build up on these things that Bögisser and the other famous people did. And we worked on this, and we had a result, and we have a result still. But then there was the pandemic. Okay, so we have this result. It was a very good, very nice result. It was generalizing all of these. It was not as far as we wanted to go. Then the pandemic hits, and we said, okay, now we have to do all these other things. We will never write it up. So we started to write an article only in 2021 after the pandemic had touched on. And the moment we are about to put it on the archive, we see, last week somebody has put an article on the archive that essentially is much better in many ways than our article. It's a complete understanding of this question that you nicely posted. So this was a little bit a bummer first, and this is the second life lesson for you to learn. If you have a result, don't wait 2 years to write it up, even if there's a pandemic in a way. In particular, not if you're a PhD student. So remember, as PhD students, as soon as you have something, write it up. It doesn't have to be published, but write it up at least, so that you then, that you have it at least. Because a lot of these discussions that we had it in 2019, but then we were like, we forgot about it, we rediscovered stuff. So it's very bad to work like this. That's the life lesson to be learned. Anyways, so we had actually looked at this result, and we discussed also with Radu, who's a nice guy. Now he's in Regensburg. And we figured out, yes, in many ways, he has a better result, but in some ways also a worse result than ours, because his result cannot be generalized to 0-1 matrices. Remember, this was Valiant's first, but ours was about 0-1 matrices. So very good. So let me tell you just the theorems that we have, because time is running. So we have two theorems that essentially go into the direction that Alejandro mentioned. It's the question, how hard is it to compute these immanents for special types of vectors? So so we have let me just so we start with the shape, and then we essentially add stuff to this shape, in both cases. And we want that the thing that we start with, the lambda d, is domino tilable. So domino tilable means that you can put dominoes on top of it. That's just a combinatorial question. And the important thing is then, both for 0-1 matrices or for adjacent matrices of edged weight planar directed graphs, so these are two combinatorial things, we can show that if you feed this into the the immanent corresponding to such characters, and you let n grow, this problem is sharp P. Okay? Very good. Okay, so I'm looking at the time. So how do you know? This is again, how do computer scientists normally prove such things? Yeah, NP hardness, whatever hardness. Exactly. So this is why I'm saying I'm not a computer. I'm a very bad computer science. Very good, because the only thing that we of course also did was to reduce it to a problem that is known to be sharp. That's what you do. Okay, for this I need to talk about something else for a minute, but this is maybe a little bit technical. Let me just talk about border strips. So this was the definition, but maybe let's just do it again at the example. So a border strip tableau is a combinatorial thing again. Now you have two partitions, lambda and mu, where one is the shape of the tableau. So in our case, it's 5, 2, 1. So I have 5 here, 2 here, and 1 here. And the other one is the filling of the tableau. That means so you associate numbers to the tableau from 1 to n in such a way that the first number appears 3 times, the second number appears 3 times, the third number appears 1 time, and the fourth number appears 1 time. Okay? So 1, 1, 1, 3, 1, 1, 1, 2, 2, 2, 3, 3, 4. And you have to do this in a way, the rows and columns, columns have to be increasing, strictly increasing, columns have to be weakly increasing. So there is some ordering on the things, and then you can, I mean, these are then all the border strip tableaus that you have. Why is this interesting? You can now calculate the height of these. This is again a combinatorial number that just essentially tells you how these numbers are into the tableau. Yes? Oh, sorry. So they have to be strict, maybe they have to be weakly increasing in each row and each column. Weakly, yeah, sorry. Did I say strictly? Yeah. Very bad, very bad. Yeah. Yeah, so the problem is with young tableaus, there's so many rules. You can build different young tableaus and count different things. Sometimes things are weakly decreasing, increase the standard young. There's a lot of mess. So anyway, so the interesting thing is you can construct these numbers of these, the heights of these things, and I think we heard about, no, we didn't heard about this rule, but this is a rule to tell you how to build the character, how to calculate the character of a element, of a conjugation class with respect to an element. So it gives you a very nice way of calculating these. So you just take all, so you have the conjugation classes are labeled with partitions, and the irreducible representations are labeled with partitions. It's very crazy now. I can feel exactly with you, Monique, that this is hard. Sorry. It's really hard to get one's head around. So there is partitions everywhere. Once because we have the irreducible representations that are partitions. The other one because the conjugation classes. So we evaluate partitions on partitions. Anyways, the important thing is in the end, it all boils down to a very combinatorial thing. So this is the nice thing about the symmetric group. Everything can be done very nicely combinatorially. Okay, maybe I skip this for a moment. Okay, so let me just talk about a little bit why I had all of this technical stuff in here. So this is the third life lesson for you to learn. You always start by thinking, oh my God, I have to talk for 1 hour. How am I going to fill 1 hour? Then you prepare all these slides, and then in the talk you realize time is much faster than you think. Anyways, so again, you start from a problem where you know it's sharp P hard, and then you have to reduce your problem to that. So the one problem for the 0, 1 is that we know that the counting perfect matches of 3 regular bipartite graphs is sharp P complete. That was 92. So the proof strategy is then just to starting with the graph that 3 regular bipartite graph, build another big graph such that the immanent of that graph would reveal a number of matchings in this graph. Okay, I say it again. You have a graph. You need an algorithm starting with the graph where you know calculating this number of matchings is hard. You say, okay, I have this. I build another graph in our setup that is bigger but in a controlled way, such that if I take the adjacency matrix of that graph, I feed it into the immanent that I want to study. I can, from the information of the immanent, deduce information of this original graph. Hence, the problem of calculating this immanent must be as hard as the other problem, right? Does it make sense? Okay. If you have understood this, then you have understood much more than you should maybe. Very good. So, no, just kidding. So, I mean, again, technically how you do this, you start with a graph and you build a bigger graph in a controlled way such that the matchings of the one graph correspond to cycles in another graph, and then you do cycle counting. That's maybe, okay. Yeah, I see, I really wanted to give you all of this thing, but I mean, so you essentially start, I mean, we start with a gadget and we replace every node by this gadget and then essentially build up a bigger graph in a controlled way. We have a fixed, I mean, we increase the size of the graph in a proportional way. So for every node, we get a fixed number of new nodes. So it's just linearly growing, but still the new graph reveals to us the new graph, the perfect matchings of my original graph and the cycle covers of this new graph that I built, they are in one-to-one correspondence. That's the key thing. And then all you need to show is that, okay, calculating the cycles of length 2 in my big graph is essentially doable with the immanent. Okay? So we start with this 3 regular bipartite graph. We take the bigger graph G and we look at the corresponding immanent. This is just immanent that I wrote down. So then, I mean, I skipped over this technical lemma. So we have exactly a lemma that tells us when are these products 0. If this is not a cycle cover, and if it's a cycle but not contained in one of these cycles, we can be sure that follows from the T theorem that I didn't mention. So that then the immanent also is 0. So essentially, and then with another part of this T theorem, we are able to say, well, there is also something that essentially gives us this identity. So the immanent essentially can be related. So everything vanishes except of that, which is essentially you can express the immanent in terms of the number of perfect matchings of H. So the number of perfect matchings of H equals this here. This here immanent times this. So yes? So the lambda is, okay, the lambda is one of the partitions of where we start with. Okay, the lambda is we have the immanent lambda. This is, and this is lambda from our, it's a little bit technical. I'm very sorry for that. And exactly. So exactly. So this is the lambda d. That's the, So the interesting thing is that we can actually relate the immanent with, this is the character of the lambda evaluated at a very particular partition and times the number of perfect matchings of H. So we're done. Are we? What is the now this is again another live lesson. What is the only thing that could be a problem now? When you have an equation like this, what do you want to do? Exactly. So the only thing that, I mean, what could be bad is, of course, I mean, by some reason the immanent could be 0 and this could be 0, so we have no information. But this is the only thing we still need to do. Okay. Then we have another theorem that says it's a non-vanishing, and it tells us that exactly on this partition here, everything is fine. This coefficient will not vanish, so we are allowed to divide by it. So we essentially get the perfect matchings of H is expressible in the immanent. And yeah, so the important thing again is the construction of this bigger graph is done in a very polynomial way, and we are essentially sure that also we can calculate this here I mean, this is something I have to calculate, And I told you quickly the number of doing this with these border heights. You have to do a little trick here to do something more combinatorial to be also able to always be able to calculate this in a polynomial time. Otherwise, it would be cheating, of course. Okay, and then we can also show that this also holds for the flipped partition. Okay, very good. So again, what do you do in the other case? What do you think? What do you do in the other case? You also find a problem that is sharply hard. And in this case, it's computing the number of matchings in planar graphs is sharply hard, sharply complete. And then again, you build a bigger graph such that starting from this graph, you get a bigger graph, you get a matrix that is exactly one of the matrices that we are allowed to look at, 0, 1 planar graphs, such that the immanent of that would reveal the number of matchings. Again, you do the fancy construction, and I don't want to scare you too much. But now the interesting thing is, so we need another additional tool that's very cool, actually. So now we have a weighted graph here, and the weight that we send to this edge is x. So if we calculate the immanent, maybe let me do this. Oof. Oof. So the interesting thing is, now if you calculate the immanent, in this case, the immanent is actually, because one of the edge weights was x. It's a polynomial in x, a univariate polynomial in x of a certain degree. Like here, yeah, so you have an x here. Now we use interpolation to get the coefficients of this polynomial. And you also have to show that the thing that you at the end get is not 0 by accident. So that you need another clever trick. And this is a trick we borrowed from this paper from Radu, that you can also show that some partition, some character doesn't vanish always. And then you can also do the same trick here. Exactly, so you do the same thing here. The polynomial, you do coefficient interpolation, and then you get that the immanent is computable in a polynomial time. Would also imply that we can get those coefficients in a polynomial time. And then you get that the quantity that we know is hard to compute is expressible in a coefficient of this polynomial divided by something. The coefficient of this polynomial we get by the immanent. So were there an algorithm that could compute the immanent efficiently, then we would have an algorithm to compute the number of the number of matchings in this graph in an efficient way, which is not possible. Oof. Again, lunchtime. Okay, again, you can also do this if you allow with other ways. But that's so. This is again 5 minutes to lunch. This is an interesting problem that I brought to you for many reasons. I think this is a very interesting playground because, I mean, you can cook up a lot of families of functions that look like the determinant. You can even look at such things for tensors if you want to. And it would be I think it would be very interesting to see why and where does the complexity actually break so that it gets hard. There is, for tensors, there's a work by Lee Heng. Yeah, I was so sorry. Exactly. Where they show that a lot of tensor problems are NP complete or NP hard only. Yeah. But I mean, I think there is not such a thing for the counting yet. So of course, if it's NP hard, it's also counting will be hard. But still, it would be interesting to see a little bit how hard are things if you generalize these to tensors, maybe. In much more generality, I think that symmetry is something that is very interesting. You will see also in Luca's talk, and you have seen in Henry's talk yesterday, is actually something that allows us to make things easier, but at the same time allows us to create complicated things very easily. I don't know, I mean, so determinant is very easy to write down. The formula everybody knows by heart, but actually evaluating it is hard because it grows with n very much, exponentially. factorial, the number of summons. So this is the crux in here, but also the symmetry, in this case, maybe the GL symmetry allows us to understand why things sometimes are easier to compute still. So this is, I mean, a very interesting, there's a lot of interesting questions that lie at the heart of these generalizations of permanent and determinants. And maybe you got interested and want to look at these during your talk. So now we're at the last 5 minutes. And I said, if you fall asleep, you can now wake up. Okay, because first of all, you can read all of these things. But more importantly, I wanted to remind you all that you will all be coming to Tromsø in February, and you will be able to see the Aurora Borealis. So if you don't remember anything from the talk, at least you should get hope to see this Aurora Borealis. And because I'm shamelessly using the last minute also to announce another thing, we actually have, I mean, in the winter, it's dark, there's just the aurora. In the summer, it's light all the time. If you want to know how to live in these conditions, you can talk to Luca or Henry about this. So in the summer, the sun never goes down. And we are having another interesting conference that maybe is interesting to some of you in June next year, not in Tromsø, but in Narvik. It's a little bit south. Very important for people who don't want to come by plane. There's even a train station in Narvik. And the scope of this conference is trying to bring together math and applied math/engineering. So we have people, fields medalists even from math, but also people that do very applied things. And the idea would be really to have an exchange there, getting to understand problems that are actually both interesting from a math point of view, but also from an applied math engineering point of view. So we are currently still planning this conference, and this is why I come to you. Mark it in your calendar, but also if you're interested in maybe organizing a stream of contributor talks or whatever, please just feel free to reach out to me, because we're in the moment of setting it up. And I think all the topics that were presented here so far, and I know what the topics of the DECs are, would actually be DCs would be very good fit in one of the sessions. So if you're interested, we could have a tenor session or anything like this. Thank you very much.
Okay, yeah, thanks so much and for making these complex things look simple. Yeah, we have comments or questions.
By scrolling fast enough. Another life lesson.
So I'm sorry, but I maybe I failed to understand the main result. So it's about immanents are hard to compute.
Yes.
Of course, there are exceptions, like the determinant is easy to compute. But now you have to speak about the family of characters, right?
Yes.
Because you are.
You're absolutely right. Yeah.
So can you show it again? Which families are, for which families it is hard to compute?
So the thing is, okay, so I mean, the way you, first of all, you're absolutely right. The way you these families is to say, well, you add columns or you add rows to them, essentially. So in a controlled way. So what we do here is we start with a small fixed partition and we just add rows and columns to it, finitely many. And then we only grow on these sides, you know? Does it make sense?
And why is the determinant then not admitted in your arguments? I mean, like what you said now would also be okay for the determinant where you have just one.
No, because we always need rows as well.
Uh-huh.
Exactly, the tile.
Where is it written? As a 1 times 2 domino tiling. Uh-huh. It's hidden somewhere.
Yeah, it's hidden somewhere.
Okay, thank you. Thank you.
So let me, I mean, one of the interesting things about this thing is actually, I mean, Alexander said, oh, I calculate the determinant because I can do Gaussian elimination. I mean, there's other algorithms to efficiently calculate the determinant by something called dynamic programming, where you essentially don't have to divide at all. So if you by some reason don't like to divide, yeah, and this uses the fact that you essentially that there's a lot of cancellations in cycles that correspond to each other. So yeah.
Yeah, any further questions? Okay, then maybe let me ask, so you mentioned some kind of that permanents come up in a lot of places, so I'm kind of naively wondering, what about other immanents?
Oh.
Yes.
So okay, this is a very good question. So all the instances I have found so far are deeply in computer science, where people even generalize immanence to fermions and so. So, but the funny, exactly, they call them fermions. So maybe this has something to do with physics. Yeah, I think for me it's just really this kind of understanding the things in between, and I'm sure you can cook up combinatorial problems that can be also. I mean, this is what we do, right? We cook up a combinatorial problem that can be calculated with immanent.
Okay, then I think we can finish here for now and reconvene at 2 and go to lunch now. Yeah, so thanks again.